Hello and welcome back. Today we'll take a look at the first law and the associated quantities, that is the energy, work, heat, enthalpy. And slowly we'll come to all of them. But you all know that Joule had shown the equivalence of work and heat, and that it summed up in the first law that the total change in the internal energy, delta U, is the change in the heat that is exchanged between the system and the surrounding, and the work done on the system or by the system. So Q plus W, right? If I were to look for very small changes in the energy, then I would just say du is equal to delta Q plus delta W. And note over here that what we write is du, whereas for Q and W what we write is delta Q and delta W. The difference being that the energy happens to be a state function, which means it depends on the state of the system. Okay, you can compare this with the potential energy. It just depends on the height of the object on the hill. If the height is higher, the potential energy is higher, right? So it doesn't matter how this fellow got to the top of the hill, but the potential energy just depends on height, the mgh that you know of. Okay, so this is a state function u, whereas q or w, heat or work, is not a state function. Okay, it is something that is exchanged when changing from one state to the other, or even changing from one state and coming back to the same state, doesn't matter. But Q and W are forms of energy that are exchanged. Okay, so they do depend on what path I follow. Okay, and that's why we cannot write du, because writing du means you can then integrate from u1 to u2, and when you do the integral, what you get is the integral which comes out to be u2 minus u1, right, which tells you exactly that u depends only on the initial and the final state. Yes, if it is not a state function, I cannot write such an integral, and therefore will not write such a dw or dq. Instead, some books would write d with a cross, d cross q and d cross w, or some books would follow delta q, delta w, and since we are following Macquarie, we would rather stick to the notation that is given in Macquarie, delta q, delta w. These are of course infinitesimal changes. Okay, all right, now to make this idea more clear about the different paths, let us take an example. We'll consider an ideal gas, and we'll consider some reversible processes. We'll take a look at two different paths. So if you see over here, what you have is a gas at point A, which is defined by P1, V1, T1, and you reduce the pressure. And of course, when you reduce the pressure, what you're doing is you change the volume also. Not in all cases, but in this first case, you reduce the pressure and you increase the volume. So the pressure goes to P2, the volume goes to V2. The temperature is conserved at T1. Okay, so there's no change in temperature, and what we call such processes is isothermal. So going from A to B is via an isothermal path, and it's a reversible path. Okay. Again, let me remind you, we're going to deal only with ideal gases. Now, for ideal gases, what we know is that the internal energy depends only on the temperature. And since the temperature does not change, the internal energy should not change. That is, delta U going from A to B should be equal to 0. Yes, delta U going from A to B equals 0. And since delta U is nothing but Q plus W, or du is delta Q plus delta W, I can write even du is equal to W, right? 0, because for each and every point over here, the temperature is held constant. So even du happens to be 0. So delta WAB is equal to minus delta QAB, right? So since this entire thing summed up has to come to 0. Okay. All right. There should be a small minus sign over here, I guess. So WAB comes out to be minus Q of AB, and W, the work done, is nothing but pressure applied times change in volume. Now this is something which I believe you all know. If not, then look at the chapter on first law of thermodynamics in McQuarrie. You could look any book for that matter, and you would get to know that the work done, okay, or delta W rather, is given by PdV. And since if I look at this curve, my pressure is going from P1 to P2, and this is a reversible curve, so pressure is going to change reversibly. The way pressure changes reversibly is that we are expanding gas, right? So outside, and let's think of one container, and it has got a piston, and this piston happens to be movable. Just like a car engine, you could think of that, you can picturize it that way. So you have this piston, and this piston is coming out, so the volume of the gas inside is expanding. Okay, it's increasing, and slowly it's coming out. And how it's coming out? By making sure that the pressure outside happens to be slightly lower than the pressure inside. Well, so slightly lower that is essentially that the pressure outside and pressure inside can be said to be equal. Okay, it's very slightly low, some small infinitesimal delta P. Okay, so pressure P, when I write WAB or delta W is equal to P, let me write something over here. Delta W is equal to PdV. Then what I know is that this particular pressure P is the pressure of the gas. It's supposed to be the external pressure, but in this case it is the pressure of the gas, because the external and the internal pressure happen to be equal. So let me write this as pressure external dV is equal to PdV for reversible change, right? Okay. Now if I go from V1 to V2, I would integrate, and the total amount of work done, which would be the negative of the heat. So work is done by the system, right? Sorry, again, this fellow should have a negative sign because that is the convention. Okay, we always put a negative sign so that when the system does work, volume increases, energy goes out of the system, so W is negative. Okay, when W is negative, then delta U decreases, so the energy of the system decreases when it does work on the surroundings. So work is done by the system because we are looking at an expansion. So heat is absorbed by the system. Okay. And that total work done or total heat absorbed, so is given by minus PdV, integrate the entire thing from V1 to V2. All right. And I can do that only because this was a reversible change. I can integrate it. Okay, if I do that integration, I can write for an ideal gas, pressure is equal to RT by V. So for 1 mole of an ideal gas, RT by V1. If you wanted more moles, you could have written in N over here. Okay, so what you get for 1 mole, the work done is minus RT1 log V2 by V1. So dV by V integrated gives you log V, and minus RT1 log V2 by V1. That is the work done for 1 mole. Okay, let me also write for 1 mole. Okay, now let us also look at another path over here. So we could rather than going isothermally, I could go from A to C via another path which is an adiabatic path, and then from C to B via another one which is a isochoric or a constant volume path. So I can combine these two, going from A to B directly or going from A to C and C to B. Remember, what we are dealing with is the change in energy, and the change in energy must be the same. Okay, and what I want to show you is that the change in energy must be the same, while work done and the heat absorbed must be different. Okay, all right. So adiabatic path. Now adiabat means that it's thermally insulated, so no heat can be exchanged between the system and the surrounding. Okay, so Q AC happens to be 0. Okay, but if no heat is exchanged, then of course the temperature cannot be conserved. So instead of T1, now it is T2, and also the pressure is not P2 but some different value P3. And I'll later show you that this P3 happens to be lower than P2. Volume, of course, is the same, V2 for point C. Okay, so coming from A to C, we have no change in heat. So du AC is equal to delta W AC, right? So the change in the internal energy is nothing but delta W. But when when it's just du, then I can always write this also as dW, because this is exactly du, and du I know can be integrated. It's a state function. Okay. Now I know how the internal energy changes as a function of temperature. I know that is nothing but Cv, which is a function of temperature itself, but we don't need to worry about that. So Cv is du by dt, right? Yes. So I know delta U AC, the change in energy, is nothing but Cv dt. Okay, so du I can get Cv times dt, integrated from T1 to T2. Alright, and since I know du is nothing but delta W or dW, then delta U should be equal to the work done. That is when I am traversing the adiabatic path. Alright, now let's look at the next one going from C to B. Okay, what you're doing while going from C to B is essentially heating the gas at a constant volume. So when you're at a constant volume, PdV is 0, so work done is 0, right? So the entire change in energy is due to the heat that has been exchanged with the surroundings, right? And I know that the entire change in energy is nothing but, so du is nothing but Cv times dt. Okay. But this time integrated from temperature 2 to temperature 1. So T2 to T1. Earlier it was T1 to T2 for the adiabat. For the isochore, it is T2 to T1. And all I need to do is to add up these two energies, right? Delta U AC plus delta U CB is equal to T1 to T2 CB dt plus T2 to T1 CB. So which should be minus of the first term. So the second term should be the minus of the first term. In total, it gives you 0. So delta U AB, which was along the isotherm, we already know because there is no change in the temperature and we are dealing with an ideal gas. So delta U AB is anyway 0. So either I go from A to B or I go from A to C and then C to B. The change in energy comes out to be 0. Okay. And the work done in this case comes out to be RT ln V2 by V1. The work done over here comes out to be CV dt. Okay. So they are two different work that has been done. Right. There is a heat also that has been exchanged in this one. Well, here this is because of the heat exchanged, and this is the work that has been done. Right. So since none of them happens to be 0, so this W cannot be equal to this particular W that is over here. So we have two different values of the work done, and so work done and heat exchanged both are dependent on the path that has been employed. Okay. Now the question is, which temperature is greater, T1 or T2? And I had told you that T1 is a larger temperature. Well, very easily looking at these things, you can say that P2 is larger and pressure is directly proportional to temperature. So T1 should be larger, and one can very easily tell you that. Yes. But why does the adiabat come to a lower temperature? Why did I not draw the adiabat somewhere over there? Okay. Now this is something very interesting and we should look at this. See, what happens in case of an isotherm? Gas expands and it does work on the surroundings. Okay. But the internal energy is the same. So if some energy is going out of the system and doing work on the surrounding, some heat is being pumped in to maintain the same temperature. Otherwise, if some energy is leaving the system, the temperature should normally drop down. But some heat is being pumped in. Exactly the same amount of heat equal to the amount of work that was done. Negative of that, but so negative meaning that the direction of flow of energy in case of work is from the system to the surroundings, and then flow of energy for heat would be into the system. And these two are both numerically equal, the work done and the heat, and that's how delta U comes out to be 0, and so the temperature is maintained at T1, right? That's your isotherm. But in an adiabat, the gas expands and does work, but no heat is pumped into the system, right? So the gas naturally cools down. because some energy is going out of the gas to the system by means of work. Yeah, and that is why T2 is lower than T1. Okay. Now take a look at the adiabatic expansion in more detail. du, and in case of an adiabatic expansion, delta Q is 0. In fact, Q is 0. So delta W is equal to du, and since I already said that du happens to be a state function, so dW should also be a state function, right? So if work is a state function, we can just write it as dW. Doesn't matter. Now, I know already that Cv is equal to du by dt, and so du is given by Cv times dt, right? For a given temperature. Yeah, Cv does depend on temperature, but we could work with narrow ranges of temperature and assume that the Cv doesn't change, but normally it does depend on temperature. Okay, so the work done, which is minus pdv, and I can again write minus pdv because I know that this process is a reversible process. It's always in equilibrium. The system and the surroundings are always in equilibrium. It's always reversible. One can change the direction whenever it's required. Now, so dW is given by minus pdV, which is for an ideal gas, which is minus nRT by V dV. Right? Now, I equate the two. Right? Cv dt is also dW, and minus nRT by V dV is also dW. So I can have Cv bar, which is molar heat capacity, dt is equal to, so I remove the n, r, so minus RT by V dV. So this is for 1 mole. This is when I compare the mole values. I can bring the T over here, and what I have then is Cv dt, Cv by T dt is equal to R by V dV. Okay. Now I have only T variable on the left side and V variable on the right side, so I can very easily integrate. Right. For a monoatomic ideal gas now, being a bit more specific over here, for a monoatomic ideal gas, what I have is Cv, molar heat capacity at constant volume, is 3 by 2 R. So instead of Cv over here, I'll write that 3 by 2 R. And you can see it's not dependent on temperature for a monoatomic ideal gas. So integrate from T1 to T2 dt by T, and of course I can bring the R out of the integral, and so it's just dV by d integral, which gives you log of T and log of V. So log of T2 by T1, R and R get cancelled, so 3 by 2 log T2 by T1 is equal to log V1 by V2. Just to replace the minus sign. And what you get is T2 by T1 to the power 3 by 2 is equal to V1 by V2. You can also put PV is equal to RT. So P2 V2 by P1 V1 to the power 3 by 2 is equal to V1 by V2, and get the V2 over there and get the V1 over here. So P2 V2 to the power by P1 V1 to the power 5 by 2 is equal to a constant, or PV to the power 5 by 2 is a constant, which we also write as PV to the power gamma is a constant, where gamma is given by 5 by 3. That is nothing but the ratio for Cp by Cv for a monatomic ideal gas, right? Right.